the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is dedicated to linear algebra students who are now stepping into determinants for matrices. By the way, this video could also be viewed by pre-calculus students because determinants tend to occur in pre-calculus as well. Just as a heads up to let you know that we've already defined the determinant of the 2x2 matrix to be AD minus BC, where the matrix itself is this one right here. So we've defined the 2x2 determinant to be the product of the main diagonal minus the product of the off diagonal. Now it turns out that all future determinants will actually be defined in terms of this one single determinant. However, if you get deeply involved with determinants, you forget that because the formulas get kind of crazy, but they're still pretty manageable, to be honest with you. But now we're going to go ahead and define the determinant of an n by n matrix. But before we do so, we need to add some vocabulary for convenience so that we're all speaking the same language. And I just want to give you the heads up. The jargon that we're going to create here, we will need when we're doing proofs. However, you often do not refer to, for example, minors when you're actually taking a determinant of a matrix. And by taking, I mean computing. So what is a minor? Well, let A be a square n by n matrix. The minor, m sub ij, of the element a sub ij is the determinant of the matrix obtained by removing the ith row and the jth column from the matrix A. Now, I want to be very clear, and actually I say this in this clarification, that this definition implies there is a way to find the determinant of matrices larger than 2x2, but I haven't actually told you how to do that yet, but I needed this definition first. Let me showcase what I mean by a minor. So here is a very general looking matrix. It goes from A11 all the way down to ANN. And if you take a look at the jth column, well, we have entries A sub 1j, row 1, column j, A sub 2j, row 2, column j, all the way down to A sub ij, that's row I, column j, and then A sub nj, row n, column j. Notice they're all column j, that's why the second index is all j in those cases. Same thing can be said for row I here. A sub I1 means row I, column 1. A sub I2 means row I, column 2. Again, A sub ij, it's right there. And then A sub in, that's row I, column n. And because this matrix has n rows, then the nth row first element is this guy, nth row second element is that guy, and so on and so forth until you get the nth row, nth column, that guy right there. Now I'm just telling you ahead of time, we can compute the determinant of this matrix A. And the notation we know we can possibly use is this notation right here. However, what if we don't want the determinant of the entire matrix A, but instead the matrix obtained by canceling out, or in other words, ignoring the ith row and the jth column? If you cancel the ith row out and the jth column out, you will still have, if you erase those, a square matrix. It will have one less row and one less column. So instead of being an n by n matrix, there'll be an n minus 1 by n minus 1 matrix, but you can compute the determinant of that new matrix. And the determinant of that new matrix we are calling the minor of the element A sub ij. And we denote that determinant m sub ij. So m sub ij is the determinant of what is left over after removing that ith row and jth column from A. Again, we still don't know how to compute the determinant of such a large matrix, but I promise you we will get there. We just need this conversation first. Now let's actually get into the definition of the determinant. And I say definition of determinant because we are literally creating a new object or a new scalar in mathematics called the determinant. It's a scalar that is associated with a given matrix. So what is it? Well, we know how to compute the determinant of a 2 by 2, so I've left that off of the screen. But the determinant of a 1 by 1 matrix A, which is this A sub 1, 1, it's just a one element matrix, is defined to be A sub 1, 1. That is by our definition. So if I hand you a 1 column, 1 row matrix A, then you know its determinant is just the value of its only sole entry. Now what happens if we have n greater than or possibly equal to 2? Well, it turns out we already know how to compute the determinant if n is equal to 2, but this current updated definition will also work if n equals 2. Now you can see, before I even read it off, that it is a very convoluted definition. The determinant of the n by n matrix A is defined to be this summation right here, A sub 1, 1, so the first row, first column element of A, times the determinant of what's left over after you remove the first row and first column from A, minus A sub 1, 2, which is the first row, second column element in A, times the determinant of the matrix when you remove the first row, second column from A, plus, notice this minus plus business, by the way. It's alternating. It starts positive, then goes to negative, then goes to positive, and then goes to negative, and so on and so forth. It just alternates back and forth. Anyhow, once we're done with the first row, second column, then we move to the first row, third column of A, take that element and multiply it by the determinant had we removed the first row, third column from A. And this process continues on and on until you're finished with the very first row of A. And you can see it, this entry right here is just saying, I have the first row element, last column element from A, and I'm gonna multiply that by the determinant of the matrix remaining after we remove the first row and nth column from A. Now that looks to be very, very hard to read and understand, but once you do it in practice, it's actually pretty easy. There is a summation formula using the sigma notation right here, and the alternating factor is built in. You can see it's -1 to the 1 plus j power. That gives it the alternation. When j is 1, we have -1 to the second power. In other words, when you first start this summation, we start with a positive value. When j is 2, we get 1 plus 2 in the exponent, which is an odd power, so therefore we have a negative coefficient from that. And it alternates back and forth based on that pattern. Now, if you've already dealt with determinants in the past, you know some things that other people do not. But for right now, I am defining this in terms of an expansion about the first row. By the way, when we work with determinants, some people do write the determinant of A, but other people, myself included, use this notation. Instead of a matrix bracket, we use an absolute value bracket. That means the determinant of A. And that absolute value bracket, or the single pipe bracket, gets kind of abused in mathematics. It's used for norms and all these other things, but with matrices, it means the determinant. Now, it would suck if I just moved forward and did not give you a single example. So let's go ahead and actually see an example. Let's compute the determinant that we're given here. Notice the vertical pipes there. It says compute the determinant. If I said compute the determinant of matrix A, it would have been written like this. Compute the determinant of that matrix. And then you would say, oh, the determinant of the matrix is, and then you would start up. Now what we're gonna focus on here is the very first row. And this will give you the algorithm for the most part for taking determinants. Now I do wanna say, if you look up 3x3 determinants online, there's a trick that only works for 3x3s. So I'm not gonna teach it because it's gonna be worthless in linear algebra, because in regular mathematics, it's not very common that you have to deal with a 3x3. So that little trick is just that, a very lame trick that only works for 3x3s. And to be rigorous about this, just so that you can see that it will match our definition, I'm going to write down the true definition of the determinant that we just created. There we go. Since we only have 3 columns, that's as far as our determinant computation will have to go. Let's insert the values that we see in that very first row. So a sub 1, 1 is 5. And by the way, let me color code things. There we go. So whenever I use blue ink, I'm just writing the entries from the matrix A. So a sub 1, 1 will be 5. We have m sub 1, 1. We'll deal with that in a moment. Minus a sub 1, 2 is negative 2. Again, we have the minor about the entry 1, 2 that we'll deal with in a moment. Plus a sub 1, 3. And again, the minor about the entry 1, 3. So something I want you to see here that most students, and actually what I do as well, is we do this. Plus, minus, plus. That pattern will be very helpful. And forever and ever, the first entry in your matrix from the first row, first column, is always associated with a plus. And then you go minus, plus, depends on how big the matrix is, but it just alternates back and forth from there. So that should be somewhat easy to remember. So it's a positive 5, a negative, negative 2, a positive 4, and you actually see that right here. But let's take a look at the minors. The minors are the determinants of what is remaining after you remove rows and columns. For example, I have this 5 right here, and I'm going to multiply it by the determinant of what remains after I remove row 1 and column 1. Well, let me remove row 1 and column 1. And you can see what remains there is a 3, negative 5, negative 4, 7. You are allowed to do arithmetic with the next step. So minus a negative 2 is a plus 2. And then we have times the determinant of what's left over after you remove the first row, second column. Well, let's take a look at that. Removing the first row, second column, you get the matrix 0, negative 5, 2, 7. Double checking my work, 0, negative 5, 2, 7, that is correct. Then we move on, plus 4 times the determinant of the matrix left over after you remove the first row, third column from A. Looking up to A here, we have removed the first row. Let's remove the third column. And you see we have 0, 3, 2, negative 4. It's a good idea to double check that your entries are correct. 0, 3, 2, negative 4, that looks correct to me. So I'll just go ahead and make this matrix reappear. Notice that we started by asking what's the determinant of this 3 by 3 matrix, and we ended up getting down to the sum of 3 determinants, but all of these sub-determinants are smaller sized matrices. They're all of 2 by 2s. And in fact, that's the pattern that will happen. So if I started with a 4 by 4, it would break into a summation of the determinants of 3 by 3 matrices, and each of those would break into a summation of 2 by 2 matrices. They're determinants of 2 by 2 matrices. And technically speaking, we really only know how to compute the determinant of a 2 by 2 matrix arithmetically. And that is just going to be, just to remind you, the product of the main diagonal minus the product of the off diagonal. So you will see a lot of arithmetic happen here. And I do actually take my time with this because as you move forward in mathematics, you get notoriously worse with arithmetic. Mainly because you just take it for granted. You end up doing it so much that it becomes almost rote. It's like driving after a while. There's so many people that drive and they're distracted because they drive all the time that they become really, really crappy drivers. And that's us. We're just really crappy arithmetists. All right, let's finish this out. So there we go. That's the determinant of that 3 by 3 matrix. And don't you worry, we will do determinants of larger matrices, but this is the basic algorithm. Start by putting that plus minus plus along that first row, and then just start covering up rows and columns. Steal the entry with the sign, so plus 5, and then cover up that row and column, and you will have the determinant of what's remaining. Again, you'll see that as we move forward. And as I implied in the last example there, Since finding the determinant of a large matrix relies upon finding the determinants of smaller and smaller submatrices, we say the definition of the determinant is recursive. Visually, it looks like this. You start with a 5 by 5. It breaks into the sum of the determinants of 5 4 by 4 matrices, each of which break into the sum of 4 determinants of 3 by 3 matrices. So you can see that you have a lot of sub-determinants going on. And each of those 3 by 3s breaks into the sum of 3 determinants of 2 by 2 matrices. And you can see that was all born of a single 5 by 5 matrix. That's a lot of computations. So it turns out while computing a determinant is actually somewhat easy to do, it's computationally very expensive. And it all boils down to just taking 2 by 2 determinants, or determinants of 2 by 2 matrices. Now, before I give you the next definition here, I just want to make a little statement that some of the definitions when it comes to objects in mathematics, specifically determinants that we're working on right now, they're given because we need them when we discuss things in theorems, but in use, we really rarely talk about them. So that's what this definition's all about. It's provided more for theorems than for computing determinants. Those plus or minus pieces within the determinant itself, these guys right here, -1 to a power times the minor about the entry a sub ij. If you glue the plus or minus to the minor itself, that constant, because it is a constant, a minor is just going to be a determinant, which is a scalar. And then the plus or minus 1, whatever that may be, times that scalar is still a scalar. So that scalar or that constant is called the ijth cofactor of the matrix A. You will see that in theoretical problems, like I said, so be aware. For an example, in the problem we did earlier, this guy right here, we had the minors, and if you computed out the minors by themselves without doing anything else, the minors were 1, 10, and -6. Those are what the minors were. Let me actually write those off to the side. And then due to the plus or minus pattern that we laid on top of that determinant, that will adjust the minor itself. For example, C sub 1, 1, which is the 1, 1 cofactor, is going to be a positive M sub 1, 1, which is a positive 1, or just 1. C sub 1, 2, which is a negative minor about 1, 2, is going to be a -10. And we call that the cofactor of the element 1, 2. And then C sub 1, 3 is going to be a positive M sub 1, 3, which we know is a positive times a -6, which is a -6. Again, this is important within theoretical discussions, but you will not actually see me use cofactors in computations. Also, to determine very quickly whether you're dealing with a plus or a minus, you would just add up the index and you'd have -1 to that power. So -1 to the 1 plus 1 is -1 squared, which is positive. -1 to the 1 plus 2 is -1 to an odd power, which will be, well, negative. So that's how you can quickly determine whether it's plus or minus, is just by summing the indices and then placing those in the exponent of -1. Essentially, if the sum is even, it's going to be positive. If the sum of the indices is odd, it will be a negative entry. And now we get to, probably with determinants, one of my favorite early theorems. It's the cofactor expansion theorem. And this is what I was alluding to earlier when I said, if you've seen determinants before, you know something other people don't. But for right now, I'm talking about expanding about the first row. Because remember, our definition of the determinant was all about the first row. Notice all our entries are about the first row, but it turns out that we could have instead done what's called expanding about any row or any column. And trust me when I say, being able to expand your determinant about any row or any column of your choice is incredibly powerful. Hint, take advantage of zeros. So the theorem reads as follows, although it's easier to do than to read. The determinant of a matrix can be computed using a cofactor expansion about any column or any row as follows. And this is where the cofactor comes into play, because it's a formalized way of saying you have that plus minus pattern. That's really a formalized way of saying it. So the determinant of A, the formula, and by the way, if you haven't noticed, I literally just changed the subscript notation here because there was a slight error in it, and I didn't notice it until I started to read it off, honestly. The determinant of A, well, you don't have to expand it about the first row. You can actually expand it about the ith row if you want to. If you do so, you're just going to add up the products of all the elements in the ith row, starting at the first column, then going to the second column, then going to the third column, then going to the fourth column. The products of those entries and their cofactors. Remember, the cofactor is that plus or minus sign times the minor, which is the determinant of the matrix remaining after you remove the ith row jth column. But the punchline here is that you didn't have to expand using the first row. Or you could instead say, you know what I want to do? I want to expand using the jth column. So again, j is going to be constant here. It's whatever column you want. Maybe you say the 15th column or something like that. And then the summation just says, okay, first row, 15th column. Second row, 15th column. Third row, 15th column. Fourth row, 15th column. And you go through and take the products of those entries against their cofactors. And remember, the cofactor is the plus or minus sign times the determinant of the matrix that remains after you remove the ith row and jth column. Now that sounds, when I say it out loud, really terrible. Most students probably have seen this already, so they're not like really super confused, other than just hoping that they don't have to regurgitate this notation. And unfortunately, you probably do. That IJ notation does come up quite a bit, at least in linear algebra. And we'll have a big example showing how to do this, and we'll do several different choices just so you get used to it. But I do want to mention beforehand, the proof for our knowledge base at this moment is too long for this video. I mean, really, it's very long for this video. Just using only our current knowledge base, it would take several pages, and I just don't think that'd be worthwhile. There are more elegant proofs that we can have once we have extra theorems in our toolbox. So compute this determinant right here. Now remember, you can expand about any row or column that you want, and I said take advantage of zeros. The very first thing I want to tell you though is that the sign of the cofactor, which again, I'm not really going to use that, so the sign that sits in front of the minor is just -1 raised to the sum of the indices for that entry. So for example, this entry is the 1, 1 entry. Add those two up and it becomes an even number. So the sign associated with that position is always, as I said earlier, going to be a plus. And this entry right here is the first row, second column. Add those two numbers up, you get an odd number. -1 to an odd number is going to be negative. And I hope you get the point, as it alternates across that first row. Now let's talk about the second row. Well, this guy right here, second row, first column. Add those two up, it becomes negative. Second row, second column. Add those two up, they become positive. And you could probably guess this would be negative, and there we have that. Now the punchline is this. If I shift those up so you could see those actual numbers, no matter what matrix you're given, no matter what size, it always starts with a plus here, and then you go to the right and down alternating. So it goes down, minus, plus, minus, plus. Let me put the minus in there. And then if I need to know how this row, or better yet, let's say I want to know how this row shakes out. Well, it started with a minus there because that's how I got there. Now I'll go ahead and fill the rest out. So that's the basic idea of the pattern. Always start with a positive in the upper left entry. Now I hope you don't mind, I'm actually going to erase all of that because frankly, it was in my way. The only one I keep is the upper left-hand corner. Remember, when you decide to expand about a row or a column, the entries in that row or that column are going to be the coefficients for your minors. So if you want to do less math, choose a row or a column that has a lot of zeros. If you take a look at all of those zeros in this matrix, probably the best choice for what to expand about would be that third column. So what I'm going to do is get my plus minus pattern into that column and then down that column. And to compute the determinant, and let's pretend as though this matrix is called A just because I need a name for it just so I can do this problem. The determinant is going to be the value of the entry times the determinant of the matrix left over after you remove the row and column that entry is in. Let me just go ahead and put a big matrix right here. Remember, if you remove this row and this column, you have a matrix that remains that's 2, 1, negative 11, 3, 1, negative 2, 1, 5, negative 2, 0, 0, negative 5, 2, 2, negative 1, and 2. However, did I really have to write that? Honestly, because I'm multiplying that by 0. So there was no real need for me to actually write that entire matrix out. But I wrote it for your benefit so you could see what we would have to do if that wasn't a 0 as the coefficient. All right, let's see what we have next. Well, we have that 2 as our next entry with a minus in front of it. In this one, I actually do have to take the determinant of what's left over after you remove that entire row that 2 is in and the entire column that 2 is in. I had to scoot that down a little bit to give myself some room. So let's go ahead and read off the remaining entries. I'm not actually going to read them out loud. You can just read them off the page. Then we move to the next term, which is a positive 0. So I'll ignore it this time because, well, there's no reason. In fact, I could just write it in plus 0 just to let you know that I considered it, but it really doesn't matter. And then move on to the minus with the 1. And because that's non-zero, I'll have to remove its entire row and its entire column and take a look at what remains and take the determinant of that. And I got to tell you, that's close to the worst possible case scenario. If I didn't have any zeros in this determinant here in this matrix, that means I'd have a lot of work ahead of me. But the fact that I do actually have a 0 in here means that I'm going to make either the first row or first column my choice for the expansion for that determinant. Anyhow, I don't want to get ahead of myself here, so let's go ahead and look at that last entry. It's a positive 0. I'll just write plus 0, but we're not obviously going to use it. And there we have it. That's our first step, expanding that 5 by 5 determinant down to the sum of determinants of 4 by 4 matrices. Again, you can ignore this 0 right here, so just pretend as though that first determinant doesn't exist. I just wrote it out for your visual enjoyment, I suppose. And now you have to do the same decision-making process with each of these sub-matrices. So I'm about to take the determinant of this sub-matrix. You want to take advantage of zeros. I hope it's somewhat obvious to you to expand this determinant about the third row because it has the most zeros in it. And while I have the yellow highlighter out, I will go over to this guy right here, and we have a choice: expand about the first row or the first column. I'm actually going to choose to expand about the first row, mainly because the numbers are larger than the numbers in the first column, and you'll see why when we take the determinants that that's probably a good choice. All right, so let's go ahead and do this. Be very, 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 very careful. That negative 2 is actually multiplying the result of this big old determinant, and that's going to be a couple steps that we'll have to do there. So let's go ahead and start. Let's find out the plus minus pattern first. Remember, the upper left element is always positive. Now I'm going to work my way down to that yellow highlighting. Now that I'm in the yellow highlighting, I'll just work my way to the right to fill it out. Now I'll go ahead and write those coefficients down first. That's my habit. So I have a plus negative 2 times the determinant of something. I'm not really too worried about that. Minus 0 times the determinant of who cares, because that doesn't matter. Plus 0 times who cares, because that doesn't matter. Minus a negative 5 times the determinant of what's left over after you remove that row and that column. Remember, that's all in a group being multiplied by negative 2. Let's go ahead and fill out these determinants right here. So for the negative 2, I'm going to remove that row and the column that the negative 2 is in. And we'll have that determinant right there. Now we go ahead and move over to the -5, which is in this spot right here, and we'll black out its row and column as well, filling in the values for the determinant. And there we go. That is almost done. We have 3 by 3 determinants left, but that's not too bad. The last one's a little bit of a pain. I write -1 times a group, but the reality is I need to give myself some room here because that is a big group. So -1 times a big group. We're expanding about that first row. Remember, do the plus minus signs. So I have +0, I'll just write that in. Normally you actually don't have to, I'm just writing it in for your benefit if it's your first time seeing this. Then minus a -3 times the determinant of what's left over after you remove that row and that column. This time I'm not going to black it out, I'm just going to do it. That's correct. Now we do the +6 times the determinant of what's left over after you remove the row and column where that 6 is. By the way, that's this here. I'm just not, I didn't highlight that the last time, but this time I had to because there are 2 6s next to each other, so I needed you to see which one I was talking about. And finally, -6, that's that last column, first row. So imagine that you're just taking this determinant right here. All right. Now you can see we do have a lot of computations. Let's see if we can clean things up a little bit. It's not really going to clean up a lot, but it'll clean up a little. Now, before you ask, do I actually have to distribute and rewrite all that stuff? The answer is no. I'm just doing that so that my handwriting doesn't look like an absolute mess to you as a viewer. But in reality, you would probably just continue decomposing these into smaller sub-matrices or sub-determinants. But I just decided to kind of clean this up a little bit. You do not have to do what I just did. Also, be very careful. There's a lot of places where you could make an arithmetic mistake in here. Or a copying mistake, by the way. That happens all the time. Just trust that I'm not making a copy mistake. I don't know if I am or not. Now we have to go through each of these and decide which column or row to expand about. Well, to be honest with you, they're all pretty terrible. So I'll highlight my decisions. So I'm going to expand this one about the first row because it has the largest numbers since there are no zeros in that one. I'll expand the next one about the first row because it has a 0 and large numbers. And I never described to you why I'm choosing rows with large numbers, but it's because I get rid of those large numbers. I move them out in front as coefficients rather than leave them inside as determinants. It's just a little bit cleaner in my brain to do that. The next one, no zeros at all, so I'll just go about the first row again. The next one, again, no zeros. Really, I don't care what to expand about. Let's go about the third row. No real reason, just because it looks different. And the last one, again, no zeros. What an annoyance, but I'll go about the third column. We happen to know the patterns are plus, minus. I hope you don't mind, I'm not going to change colors here. Plus, minus, plus, minus, plus, minus, all that fun stuff. Always plus starting in the upper left-hand element or entry. Plus, minus, plus, minus, plus. And then plus, minus, plus, minus, plus. All right, not that I'm excited to do it, but let's just go ahead and start. This is going to be 4 times the quantity. -3 times the determinant of 1, 5, -1, 2. -6 times the determinant of -2, 5, 2, 2. And +6 times the determinant of -2, 1, 2, -1. And that is the very first group's expansion. And we still have to do the AD minus BC, or product of the main diagonal minus the product of the off diagonal on each of those. -10 times. This time I'm just going to let the film roll as I do it. That one's actually pretty easy because we had a 0 in there. And by the way, this is a +3 as a coefficient because it's a minus. All right. I don't think there's any other caveats from this point forward, so I'm just going to go ahead and let it run. All right, sufficiently ugly, and we're not done because for each of those we have to do, again, the product of the main diagonal minus the product of the off diagonal. How fun is that? You know what I might do is I actually might pre-compute these. All right. So you can see there's only one that disappears. That's 2 minus 2, the third one in. Let's go ahead and rewrite all this fun stuff. All right. Barring any arithmetic mistakes, as I always say, let's go ahead and compress this a little bit further. Again, barring any arithmetic mistakes. Continuing forward. And that is the value of the determinant, and it looks pretty terrible. So you would never really want to take by hand the determinant of a 5x5 matrix unless it was a very special kind of matrix. Now, a lot of people watch something like this and they're like, oh my gosh, can't I just use a calculator? And generally speaking, the answer to that is yes. You can use some type of technology for very large matrices. However, you still need to know how to compute a determinant by hand because you're going to need that for the theory in linear algebra. So on a homework that you're working on or something like that, as long as it's not like a 6x6, it's good to do just one 5x5 by hand. Definitely do a couple 4x4s and practice 3x3s a few times, right? Just so you get used to taking determinants and making right choices. If you're a programming major or a computer science major, you will develop algorithms that will choose the best row or column based upon sparsity, or the fact that there are zeros there. And you also have to take into account floating point arithmetic errors that can occur because of computers, and so there are some other issues that come into play. Humans are much better at math than computers. Now, I did say that this would be a terrible matrix to compute, or larger matrices would really be hard unless they're special. And that leads us to the second to last page here. In the book that I use, it's called Theorem 2. It is one of the most important theorems to deal with matrices and their determinants. If A is a triangular matrix, then the determinant is just the product of the entries on the main diagonal. That's it. I was going to do a proof of this, but I'm already knee deep into time on this video. I will say the proof just involves a proof by mathematical induction. So if you have it as a homework item in your course, that's how you go about it, mathematical induction. That being said, I have a last final example here. Compute the determinant of this triangular matrix. Let's go ahead and create one. All right, that is an upper triangular matrix. It is square. I promise you it's a 6x6 matrix. And by the last theorem, the determinant is the product of this main diagonal. That would be -1 times 1 times 1 times 5 times 21 times 1, which is -105. You thought you were in for a big problem, didn't you? So yeah, this is great. If you can get a matrix that is triangular in form and you're asked to take its determinant, you have all the luck in the world with you. And this should start getting you to think about, well, if I'm asked to take the determinant of some given matrix that's not triangular, could I get it into triangular form? Does the determinant change as I try to get it into triangular form? Because I would love to get a large matrix into triangular form so that I can take its determinant. It would be much, much easier to do that. And there are ways to do it. We'll talk about that in a future video. All right, so I hope that most of this video was enlightening to you, and I hope you have a wonderful day and have great success in your linear algebra course. Be a good human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much, that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry. Don't